So today's webinar is going to be the last webinar for 2022 for Exida. And our main focus today is mainly on a very small part of the alarm management lifecycle. It's only going to be on the result of the alarm rationalization, which is basically a database, and then how we can use data visualization skills on that database so that we can do review on the rationalization process itself, and also trying to plan for subsequent activities based on the life cycle that's laid out in the ISA 18.2 industrial standard. So before I go into before I start everything, let me introduce myself a little bit to you guys. So I'm Paul Chen. I was based in Hong Kong in the Asia Pacific region. You might find it a little bit strange that you see my resume there. I actually had a bachelor in biochemistry and also an MA in English Literary Studies. Believe me, I couldn't find a job with these 2 degrees when I was back in Hong Kong. Sorry. But under very weird circumstances, I was actually invited by Exida to be a scribe because of my good English for a HAZOP and SEAL selection workshop in South Korea, in Seoul. And for those who don't really know much about functional safety, the HAZOP and SEAL selection workshops are basically risk analysis workshops, specifically for industrial safety systems. We try to derive a risk target as a result of these workshops for the safety system within these industrial sites. So during the workshop, I was able to basically demonstrate how versatile I was. I was very quick to be able to pick up a lot of the chemical engineering concepts, and also was able to read those piping and instrumentation diagrams within 2 months while I was on job for that workshop. And that workshop lasted for 3 months in South Korea. And that's why I was hired as a technical staff, as a technical process safety guy in Exida. And after I was hired, joining Exida, I was heavily involved with a lot of the risk calculations using Markov models specifically for safety systems. And that's what we called SEAL verification or SEAL calculations. And because of my demonstration of my skills in math, I was actually recognized and also transferred to the headquarters here in the US. And after coming to the US, I also get in touch and also get involved in other part of the business, like the cybersecurity audits project for industrial control systems, and also, very importantly, the alarm management projects. And because of the alarm management projects, usually they involved a lot of data, alarm data and databases, I was also introduced to data science as well. So that is a very brief introduction about myself. As I've mentioned about my work, that is actually the main 3 views of what Exida does. Functional safety, which means the automation, the design of the automated safety system in industrial applications, and alarm management. All the alarms within control system, we try to manage them efficiently. And cybersecurity for industrial control systems or industrial applications as well. And Exida is basically a bunch of different consultants. We are a big consultancy agent that's scattered around the world. As you can see, all these different dots on the world map. And our business are mainly focusing on 3 different areas, specifically for the customers as well. The first area is about our software, that we have our own tools, that we sell our own tools, especially the Excellencia, which is basically a suite of different modules to help you to be compliant with IEC 61511 and IEC 61508. for process safety systems, within which there's a module called Silver. So the Silver module is basically going to help you to do calculations for a risk target or risk affirmations using Markov models. So you don't really need to understand the math behind to actually do Markov model calculations. You can just use our tools to do that. Well, if you understand the math, of course, you can use simply using a lot of different matrices, because that's basically what Markov model is, and you can use Excel to do that. But for a lot of the chemical engineers, of course, the easier it would be to basically manage all the different activities within the management. So they do prefer to use our tool for that. And other than having our own tools, we also do certifications for different instrumentations, different devices, and also personnels. So we have personnel certifications, that's CFSP and CFSE. After you have finished the exams, which is not easy, there are a lot of people that actually fail the exam. You're showing your competency in working in this functional safety field. And of course, as I've mentioned, we are consultants. We also provide expertise on different lifecycle services. So why do we focus on life cycles? Because any kind of IEC, ISO, or ISA standard, especially when it's related to risk, there is always going to be a life cycle. And that's also something that I'm going to talk about today as an introduction to alarm management as well. So in order to be compliant with the standard, we have to understand how the life cycle works, what are the details that goes into different life cycles, what are the activities, or what are the different proofs that you are following, that basically proving that you are following the life cycles as much. So we do consulting work on that. So that is the main gist about Exida. Let's go into the main course today. So our main course today is about alarm rationalization. If you are not familiar with alarm management, you probably do not understand what even this term means. So let's take a step back. What exactly is alarm management? The main aim for alarm management is to optimize your alarm system. Why do we need to do that? That is because there were a lot of alarms, and there are usually a lot of alarms that already exist in your systems in the software layer. Because right now, all the alarms are basically like a software data point within your control system. But back in the 50s or 60s, most of the alarms are basically hardwired. I've actually been to a really old boiler system in Canada, in Saskatchewan, where they still use alarms as like a flashing light with sirens, and everything is hardwired within that, and they do not have like an interface to interface with that. Every interface would be something that's bleeping on the panel that you can see physically. So back then, because all these are hardwires, so all these are actually easier to manage. Why would that be the case? Because right now, everything is in the software layer, and there is a false concept from the manufacturers that they think that, okay, more alarms means safer plants, safer site. So they just set everything up on default or by the manufacturers, and no one actually reviewed them. So that ends up with a system with so many alarms, and that's why we have situations like more than 1,000 alarms per day, and within 10 minutes we have like 9 alarms coming in bleeping at the operators, and they do not know what to do. And we have alarm flood situations where suddenly there could be more than hundreds of alarms coming in just within a very short period of time. And also, very importantly, there are situations that because within the control system, in most all the control system like Delta V, Yokogawa, they have something built in called priority. The original intent of the setup of the priority is that different alarms are basically divided into like low priority, medium priority, or high priority. And when a low priority and a medium priority alarm come in at the same time, the operator should always handle the medium priority first. So, but because no one reviewed these priority settings within the control system, so most of the alarms are actually set up by default as high priorities. So in that case, there's a very high chance when two alarms comes in at the same time, they're all both high priorities. So in that case, that the operators basically, they don't know how to handle them. And that's why we need a proper system there to handle and manage these alarm systems properly. And as I've mentioned, anything that's related to risk analysis, usually when it comes to standard, there's a life cycle. And what does life cycle means? Life cycles is trying to describe the life of something. And here, specifically in the ISA 18.2, we're describing the life of an alarm system from its birth up to its demise, decommissioning of this whole system. So we are going to focus mainly on the top 4 activity within the life cycle. The first thing we're going to talk about is the philosophy. So the philosophy is basically the blueprint for everything, because we need to have a plan to start everything, to give birth to this whole alarm system. It is a guide for all the different activities within your management cycle. It should be providing goals and targets for your alarm system so that you can follow up and then try to do assessment to see whether you have reached the proper optimization of your alarm system. And also it lays out roles and responsibility and also maintenance plan for the alarm system as well. So after finishing this blueprint for your alarm management system, we basically go into the control system and then try to identify all the potential alarms. That should be fairly easy. Why? Because everything is set up in default, so we can basically download all the data points from your control system, and those are all the potential alarms that we need to review. And then we go into the most important activity in the alarm management lifecycle, which is the rationalization. So what exactly is rationalization? So the whole flow, the workflow for the rationalization is that you bring in someone who knows about alarm management, who knows about these kind of system, how the ISA standards mandates different activity in the system, in the whole life cycle, and then basically try to help the plant, the site, to be compliant with the ISA standard. And this person would be the facilitator for our rationalization workshops. They go into the plant and then they meet up with different peoples, process engineers, control engineers, process safety engineers, operators, supervisors, maintenance people, instrumentation guy, and maybe other kind of engineers as well. And then they discuss for every single alarm that we have identified within the system, and then review every little aspect of for features or settings that are related to that particular alarm. For example, the causes for the alarm. What would be the consequence if the operator ignore the alarm and then let the situation escalate? What are the actions that the operators need to do to clear this alarm and prevent the consequence? What are the urgencies, the time to respond to that particular alarm? And also try to understand what severity that's related to the consequence. And then from that, we can derive the priorities, and also we can also understand what would be the set point, trigger points for these alarms as well. So after knowing all these attributes for one alarm, we put them into the record. And then for each of the alarm, we review all the different settings and all these different attributes as well. And after finishing all the reviews, we basically create a database. And that database is termed by the ISA standard as the master alarm database. It is a database of an authorized configuration of your alarm system for all the alarms in your system. And that is the output for the rationalization activity. And after we've finished the rationalization, we go into the detailed design phase. So what exactly is the detailed design phase? So the main gist of it would be activities related to the HMI interface design, which is basically the UI interface for the operator when they try to interfere the process within the plant, like how the different equipment is being shown, what the valves or maybe reactors or agitators, different controllers over there. So this is an example of a HMI design, an HMI interface. Not a good design though. So other than the HMI design, we're also going to try to understand the alarm summary display as well, like how the alarms are being displayed and being communicated to the different operators in the plant. But our main focus today is going to be the advanced alarm design. So what exactly is advanced alarm design? So by the standard, it means that it's some kind of a programming, some kind of layers of logic or modeling to basically modify the different alarm attributes or different alarm settings in order to help with situations like alarm flood or some kind of nuisance alarm coming up at the same time. So let me give you an example, a very simple example, what it means by advanced alarming. So one of the example that we can do with advanced alarming is suppression by design, suppressed by design. So what we're trying to do here is basically try to suppress the alarms. So let's think about a compressor. A compressor usually has a lot of different alarms associated with it, like vibration alarms, flow alarms, or even pressure alarms or temperature alarms. And if you know about compressors, usually when there's some problem, all the alarms would come in at the same time because vibration would be related to like overloading of the whole compressor. And when the compressor overloaded, it will basically increase the bearing temperature, and then the temperature alarm would come in at the same time. And because of temperature going high, the pressure, outlet pressure will also go high. So every different alarms would come in at the same time. So by suppression of design, we can actually do something like we basically try to identify all the alarms as associated with the particular compressor, and then put them into one group. When one of the alarm comes in within that particular group, one alarm within the group is triggered, then we suppress the rest of the alarms within the group until that particular one alarm is basically cleared. So in that case, we won't have like 10 alarms coming in at the same time in a way that the operators don't really understand what actually is the root cause, because usually the alarm that comes in first is the root cause for the situation. And if you're interested in root causes, I actually made another webinar about root cause I think within this year, but it was several months ago. You can look up in our YouTube channel and then have a quick look into that particular webinar that I made. So that is the main gist and main example of a suppression by design, a kind of advanced alarming. Now let's go back to the life cycle. So what we try to do today is trying to basically relay the philosophy and do the rationalization and then find out what to do within the detailed design over there. As you can see, because rationalization is basically kind of a sandwich between philosophy and also detailed design in that sense. So what we want to do is to understand what information and analysis that is set within the philosophy that we have done based on the data that we have after the rationalization, the database. We do some that we can do to do the analysis to relay and also affect the detailed design that we are going to design for the advanced alarming design. And what kind of data visualization that we can do and that can help us with the analysis. Specifically, what we want to look at would be the priority distributions. And we are not just looking at priority distribution across the whole plant. We're also going to look at distributions within each unit and also different distribution and in relation with their alarm types. And also we want to look at all the non-alarm class priorities and their alarm types as well. I will go into detail when I showcase the visualization draft that I built for one of the refineries project I did in the past. So now we go into the data part for alarms. So as I mentioned, the result of alarm rationalization is basically a big database that contains these different datas. Since we have different datas right here, why don't we try to basically do some analysis using those datas? So the usual way how we do analysis is actually try to plot charts with them. We do data visualization. So we have different charts, we have different ways to look at data and understanding the meaning of these or implications of what these data tell us in a way that it can provide some kind of insight. And data visualization is basically that. We plot everything into something that can be visualized. And during this process, we usually employ a kind of analysis process that's very popular. That's called EDA, Exploratory Data Analysis. So what exactly is exploratory data analysis? It's basically using a lot of the basic statistical concepts like means, mode, or medians, and then try to use that to basically visualize these kind of result of the data, and then try to understand the different characteristics of these data so that the characteristics can actually provide some kind of meaningful patterns. And when these meaningful patterns comes up, we can actually try to provide some kind of models and strategies that we can use when we try to do other kind of analysis, especially when we try to do predictions, like using machine learning algorithms to do predictions. So let's see how exactly this process is going to fit into the data science process. So the data science process, as the title suggests, is mainly to deal with data. So we have data from the reality, we extract those data, and then we try to process the data to do the data cleaning process. And during the data cleaning process, we try to design and do something called a Bay feature design, which I will talk about in the next slide. And then after the data is cleaned, we go into the EDA process. Within the EDA process, we plot graphs and do analysis, and then we can build some kind of insight so that we can pass that into different models or machine learning algorithms to do the analysis. And sometimes we can even skip this process and directly do these kind of visualized report And then based on this visualization, we can make decisions. And today, I will be mainly focusing on just directly going into visualization and then making decision based on that, instead of talking about machine learning process. Machine learning algorithm is a really big process, and there's so many different models with so many maths. In 10tel, I would find some time to talk about that in the future, but definitely we don't have enough time today. So as mentioned, there's something called feature design when we do the data cleaning process. So basically, during the feature design, we try to combine different parameters and features into new features. For example, like we can combine different alarm attributes and then basically produce a new kind of parameters for those attributes. And that is a process called feature engineering. And I will give you an example when I do the visualization example for the refinery that I did. So before I go into my own visualization example, I would like to at least introduce you to some of the visualization functions within your control system. So within different control systems, they already have some built-in visualization functions. And this is from the Delta V control system from Amazon. The first histogram here is basically showing how many alarm triggers over a period of time based on their different priorities over there. And the pie chart here is basically showing the priority distributions, which basically means that how many alarms are actually, of what percentage are actually taking up the number of total alarms out there based on their different priorities out there. As you can see, these analyses are really actually quite, I would say, not exactly that primitive as a derogatory term, but it's not going to be enough when you try to design some advanced alarming programming situations. These information is not going to be enough for that. So that's why when I do visualization, I would do something that's a little bit more in-depth, a little bit more advanced than what's being shown from the innate program or functions from the industrial control systems. So what I do is that I use the database, master alarm database, and create some Tableau function based on that. So let me show you the Tableau that I made as a draft for one of the refinery that I did in the past. So this is the a draft for one of the Tableau visualization I did for one of the refinery up in the Rust Belt region. So as you can see, it's like an infographic. For the basically for different stakeholders to look at, for different engineers to look at, even for the management to look at as well. The main thing that we want to look at would be, first of all, as I mentioned, the priority distributions. So as you can see, there are 3 different priorities here. So within Delta V system, they name the priorities instead of high, medium, and low. They name it as critical, warning, and advisory. So critical is high priority, warning is medium priority, and advisory is basically low priority out there. And immediately you can see there are problems within this distribution. Because this is a resultant priority distribution from a rationalization. So all the review has been done. But we are actually having more alarms than the targets that's set out within the IEC standard. And that is going to be a problem because when we get into a situation that we have 2 alarms coming in at the same time, that means that there are higher chance of them coming in as high or medium priority at the same time. So that is going to create stress for the operator. And also it's also another problem is that you see the advisory is actually falling short of the target within the philosophy as well. So that means that for the low priority alarms, we actually falling short in terms of the percentage, how much we want for the total number of advisory alarms within this system. So that is the total number or the total priority distribution for every alarm across the whole system. Now let's look at each of the subunit and units. In order to visualize the priority more efficiently, I created a new parameter when I try to visualize them. So this is called alarm priority number, which I named it myself. So what it means that is the summation of the priorities within each unit or each subunit. What does that mean? So I assign a number to each of the priority up there. For critical, I assign number of 3. Warning, I assign a number of 2. Advisory, I assign a number of 1. And then I add everything up, the total number of everything for each of the unit. And each of the unit is basically, or each of the subunits is basically being shown as one of these bar over here, as you can see. And immediately we can identify 3 main problematic subunits out there. As you can see, the bars are really high, and also they are of a different color as well. So this is another skill that you need to, I guess, anyone that's dealing with data visualization need to know, is that how we can actually highlight informations that basically deserves our attention in that sense. And from this little round chart here, we can immediately identify the 3 problematic units. And for these 3 units, what exactly are the problems? So these 3 units are the MAC units, the ROSE unit, and the different boilers over there. So let's look at the MAC unit first. The MAC units consist of 3 different subunits: the MAC main, the MAC flare, and the MAC tank. And if you are familiar with the with any kind of a chemical processes, you will understand anytime the flare comes up with alarms is actually not a typical situation. When the flares has an alarm, that means that it's really serious problems. So therefore, our main focus would be on the MAC main here. And when you look at the distribution, you do realize that the MAC main, the critical alarms, and also the warning alarms are actually of quite high distribution over there. They are taking up about 50%, the same as the advisory alarms over there. And that is going to be a problem for the operator. As I mentioned, if 2 alarms comes up, they would very well be in the critical or the warning situation over there. And this is even worse in a sense that because usually for each of the refineries, they divide operators in different groups. And each group is usually going to handle 1 unit at a time. And for each group, they're usually only 1, or sometimes if they have enough manpower, they have 2 operators on duty for each of the unit. And considering that there's only 1 or 2 operators when they have any kind of process upset, and they may have about 10 alarms coming in at the same time, then 10 alarms are coming in both as a critical or warning. That's going to create so much stress for them in that sense. So that's why we need to look into the system for the Mac system and then try to understand whether these alarms are they actually associated with a specific equipment. Maybe we can do what I mentioned before, suppression by design. Try to group these alarms together and then try to troubleshoot in that sense. Or maybe even we can just try to re-rationalize this particular unit. And maybe even when we see these in situation over there, that might be a kind of indication that we need to redesign the pipeline so that we can avoid the point of using alarm to provide these kind of protection as well. So these are the insight and the output of this data visualization for some kind of subsequent activities, either for the detailed design or some kind of review, or even for other kind of design, even specifically for the process itself as well. Now let's move on to the next unit, the rows unit. It's actually more problematic in a way, because if you look at the rows main here, they have even higher proportion of the critical and also warning alarms. So because main would be the ones, most of the alarms where they actually comes from, or in a way that they have a higher probability of coming from as a source for the alarms. And the other problem that I see from this is that we have something called rows loops. So loops within refinery or within any kind of I would say industrial control system, usually they are referring to what we call interlocks. So what exactly are interlocks? Interlocks are automatic functions that's set up within the system that when they detect, for example, like a high pressure situation, and then it would directly try to close some valve or stop some pump so that it can avoid that high pressure situation to further escalate. But because these are automatic functions, that means that usually there is no action pending from the operator because the system can take care of it itself. So in that case, usually these loops would actually, or interlocks would actually need to be like a notification. They shouldn't be an alarm for the operators because the operators can't do anything about them. So that is something that we definitely need to go back into the system and then try to discuss with the operator about how exactly we can change that. We do need to do another rationalization for this particular unit to troubleshoot that. Now, let's move on to the next problematic ones, which is the boiler. This one is actually a little bit easier to look at because most of the alarms are actually going to be in the boiler D. So maybe the boiler D has some kind of a problem with the design, or maybe it's more important of the process situation over there. So most of the alarms are going to be the warning alarms. So we basically go into the unit and then try to review whether we can group some of the alarms together or whether we need to redo the rationalization again. So that is, as you can see, these kind of visualization and the kind of a story that we can gain or insight we can gain from the data visualization when we try to create a new feature and then we try to look at it in that sense. So that is about the alarm priority number. Now let's look at the result of the different alarms that are related to the different alarm types. So I created a word cloud here for any kind of alarms that are with priorities of advisory, warning, or critical. That means high, medium, low, in a way that how they are related to different kind of alarms types. And for any kind of word clouds, the bigger the font, the higher the count, the higher the number of it. would be. And you can see that most of the alarms are actually high alarms or low alarms. So that means that they are either pressure high or pressure low, or temperature high or temperature low. So this is very logical because they are very important process alarms. So they're usually, they stay within the system as alarms, and that's logical. But I do see another potential problem here, which is like the device communication, device maintenance, device fails, and device advisory. So these alarms are related to maintenance. In some of the refineries, the job duty of the operator is actually, they look at these kind of devices, communication or kind of diagnostic alarms, and then once they see these alarms, they just need to alert the maintenance team for any kind of maintenance issues. So that in a way that they actually need these alarms, because the operators need to do something with these kind of alarms. But in some cases, in some other chemical plants or newer chemical plants, usually the maintenance team can directly access these kind of diagnostic situations, diagnostic informations. So when that happens, we need to consider whether we basically remove these alarms from as an alarm, but rather try to substitute them or maybe change the type into something called a notifications. And that's something that basically means that it's a notification to the operators, and it's not going to be appear on the alarm list, so that it's not going to distract the attention from the operator as well. So these are the different alarm types that are associated with alarms. Now let's look at the different alarm types that are associated with notifications. And right now I'm not using word clouds here, but rather using these kind of bubbles here. The bigger the bubble, the higher the counts of these kind of alarm types. So let's first of all look at no alarms. So what exactly is no alarms? No alarms means that these alarms are being removed within the rationalization workshop. They are basically being disabled within the process. They are deemed to be not an alarm that's useful for the process. So when you look at these, most of the alarms that are being shut down are high alarms or low alarms. These are logical because usually high alarms or low alarms are duplicates of high or low alarms. Why? Because the way, this is basically how most of the control systems are set up. When you have a high alarms like pressure high alarm, you usually also have a data point that's called a high alarm, which is at a higher trigger point than the high alarms. And since these are of a higher trigger points, so usually they are actually a kind of a duplicate with a high alarm, because they have the same cause, they have the same actions. So if you handle the high alarm efficiently, then you actually don't need a high alarm to do that again. And redundancy of alarm for operators is something that the ISA standard frown upon. We should not consider redundancy for human perceptions, because that is only going to create a situation we call the boy who cries wolf, where you just getting numb to the alarms in that sense. And other than that, we also see a lot of the low alarm, high alarm, and this deviation alarms being removed from the system as well. So this is a very good indication that this is probably the first alarm rationalization that this site has been through. Because if they have been through rationalization before, or they have some kind of alarm management already, that means that they should have already removed a lot of these nuisance alarms already. But so when this is the first time they go through the rationalizations, they basically realize that, okay, a lot of these kind of process alarms are actually not really helping the operators, so that they just remove these alarms during the rationalization process. So as you can see, using these chart, we can actually tell another story. from the rationalization process as well. So that's about the no alarm types. Now let's move on to the interlocks alarm types. So interlocks, as I mentioned, basically means automatic functions. And as you can see, most of these alarms are actually high alarms or low alarms, because that means that when the high alarms is being ignored, or the low alarms being ignored by the operators, then the high alarm trigger point is going to trigger some kind of automatic function so that it will allow the system to handle it just itself, some kind of a automatic system to handle itself without the input from the operator, as in like a backup in that sense. And therefore, these high or low alarm trigger point are going to in line with those kind of automatic function set point as well. So in that case, that these are basically thresholds for interlocks, and that's why they are usually being removed from the alarm list, but being put and substitute into the interlock notification list in this sense. So this is the basic gist of the alarm visualization. At least this is the draft that I have done for one of the refinery that I've done in the past. I plan to add more visualization into the chart in the future, but as of now, these are quite sufficient because they're telling us a lot of different stories and telling us a lot of tasks and future work that I need to do for the whole alarm system to follow up on the rationalization process. And these can also actually show some of the key success that we have done, like removing a lot of the alarms from the systems, nuisance or useless alarms, like we probably just the low, high, and deviation alarms, we remove about like 6,000 alarms from the system. That in a way that you can tell the management or the stakeholders that we have properly organized our alarm system in that sense. So as an infographic, it's going to tell us a lot of story in that sense. So that is a very basic gist about the data visualization when it comes to the visualization of the master alarm database. The other part of data science that we usually want to go into is about machine learning models, which I mentioned that I will not talk about today. And also machine learning models, the main focus of that or main use for that is not just for analysis, but also very much about predictions. I will find some time in the future, probably next year, next year, to basically talk and select maybe one of the machine learning models and one of the machine learning algorithm, and then try to do some predictions on some safety data or alarm data, and then try to introduce you guys to the kind of horizon that we are able to basically look at and also contribute using these kind of machine learning models to facilitate the whole safety process in that sense. So if you guys are interested, I really advise you to join our course. We have different courses on different aspects of functional safety and also on cybersecurity and also about alarms as well. If you want to know more, welcome to join our discussions in our LinkedIn, Facebook, and Twitter. And I will try to answer some questions right now. But I also have an email right there. And welcome. Also go to my LinkedIn profile and maybe ask me a question over there as well. I'm also available on the LinkedIn. So if you want to write me questions, I'm also good with that. But right now, let's see what kind of question we get. So I have a question about alarm rationalization itself. So it's asking, do you see any kind of value or feasibility of conducting during the design phase of your, basically of your alarm or your system, or kind of a lack of information from the plant that does not allow this kind of information. So basically, it's asking whether we have any kind, if we do not have any information as input for the alarm system, then how can we actually start that? In a way that I think that's what he's asking right over here. So my understanding is that usually alarm rationalization is a process that you can do after you have done your hands-on, your process hazard analysis, in a way that you basically have a lot of information, like what kind of alarms as safeguards, and what kind of alarms are IPLs, and also because during the hands-off you should have PNID as well, so you do have some of the alarms that's already within the PNID as well. But I would really advise you to see if you can find the control system first, because there are a lot of hidden alarms within the control system, so that you can have a better picture in terms of what are the potential alarms you want to rationalize during the rationalization process. Hope that answers your question. So another question is about what kind of software we can use for alarm rationalization. So we do have our own software, which is called Seal Alarm. The main key strength of Seal Alarm is that our Seal Alarm is designed according to all the data input and data requirements based on the ISA standard. So when you use that software, Seal Alarm, you basically compliant with the ISA standard, and they also provide an easy workflow for that. So that's why we design our software in that sense. There's also it's not a question, but some suggestion, I think. It says, please be aware that when you do alarm rationalization, that you will also move alarm to priority 3 to priority 2, and also priority 2 to priority 1. So that is very true, yes. When we do alarm rationalization, we are going to review all the priority settings within the within your alarm system. And the way how we actually do that is to review the severity as well as the urgencies, and then based on some matrix we can do that. If you are interested to understand how exactly we are to derive that priority, welcome to look at other webinars that are done related to alarm rationalization. I believe any alarm rationalization webinars out there that's either done by me, Paul Chen, or maybe by Todd Stauffer, we talked about what exactly priority means in that sense. So I apologize because we don't have enough time anymore. So maybe if you have further questions, welcome to write me an email, or maybe message me on LinkedIn. I'm really happy to answer you any questions. And I really hope everyone can enjoy the holiday season. This is the end of year, so I really also hope that everyone will have a brilliant next year and face all the new challenges and be well for 2023. Thank you very much, and I'll see you next time.